My name is Qian. I'm from Beihang University, China. It's my pleasure to chair this session and introduce our first keynote speaker, Professor Hongbo Fu. He is a professor in the School of Creative Media, City University of Hong Kong. He has been actively working on projects in the fields of computer graphics and human-computer interaction. His work has been selected as the program highlights by SIGGRAPH and SIGGRAPH Asia multiple times. Okay, let's welcome Professor Hongbo Fu to give his talk, Data-Driven Sketch Interpretation.
Okay, hello everyone. Good morning, good afternoon, good evening, and yeah, thanks for the kind of invitation to give a talk at this workshop. I think it's quite meaningful workshop. Yeah, thanks for the great efforts for organizing this workshop, and also thanks for the introduction by Chen. Yeah, I'm from School of Creative Media. This is kind of an art school, but currently we also have a pretty decent team working on the topics related to graphics and HCI. I'm going to talk about sketch understanding from a graphics point of view, because mainly I'm working in the area of computer graphics, and I consider sketching is a very important control mechanism for content creation, for example, for 3D modeling and for image generation. So as you know, sketching provides an easy way to express ideas and also to depict the shape and the form. So human viewers can easily understand the complex shapes sketched through sketching. So a commonly asked questions in the research community is whether machines can also learn how to interpret the sketches as human viewers do. And this is, as you know, it's quite challenging because sketches are often very sparse, have very limited information. So the sketch understanding becomes ill-posed problems, and the sketches are often exhibit different levels of abstraction and deformations. And to answer this key question, and we need to solve a few key sub-problems. For example, given a sketch, what a sketch depicts. So this is kind of like sketch recognition problem or sketch classification problem. And second, what components constitute a sketched object? So this is kind of a sketch segmentation and the labeling problem. And third, what is the underlying 3D shape? This is a problem of 3D interpretation. And lastly, what is the underlying photorealistic object? And this is as kind of sketch-based image generation. So in this talk, I'm trying to talk about my attempts to those questions. And all these problems are generally ill-posed, and because yeah, Sketch basically provides a very limited information, so we need additional cues or information to make those problems just solvable. And fortunately, such cues might exist in existing data in the form of sketches, images, or 3D models. So that's why it's possible to develop data-driven approaches to those problems. And first, I'm going to talk about data-driven sketch recognition. I think more rigorously, I think this is a sketch classification problem, because the goal is to classify what a sketched object is, instead of really recognize a specific instance of an object. So, for this problem, I think for other sketch understanding related problems, we have a few very important data sets, including this TU Berlin data set. And also recently, there's a quick draw data set by Google. And this quick draw data set is a much larger scale, and but contains more abstract or doodling sketches. So the first, I think not the representative solution to this sketch recognition problem is SketchNet by Qian et al. Also Song's group as well together. It's a joint force. And so their solution is based on a deep CNN model, and they take a sketched image, bitmap image, and then the beauty of the solution is to kind of like they provide a very nice data augmentation approach, and they use stroke removal to try to handle different levels of abstraction, and then sketch deformation to handle different levels of deformation. And so they achieved, the approach achieved quite impressive recognition accuracy, and for the first time surpass the human performance on the T-billion data set. So their solution takes a sketched bitmap image as input. So our group developed another solution. We try to take this problem just from by taking the structure of the sketch, and typically sketch often have the strokes. How can we use the strokes, the information in the strokes to solve this problem? So we have this sketch R2CNN to be published in TVCG just very soon. And so the key idea is quite simple. Given the sketch vector-based representation of the sketch, we try to encode the relative positions, and then through the RNN, and we can get the point features, and then with the encoded per point features, and we fuse them with the original vector sketch, we get multi-channel point feature map, and then we pass the information, the multi-channel point feature maps to CNN for classification problem. And generally, we achieve a better performance. There's a chat.
There's nothing important so far, sorry.
Oh, okay, and sorry. And then, yeah, we can achieve, I think, the state-of-the-art performance, and we show, okay, the introduced RNN model and generally can perform improve the performance with the existing CNN-based backbones. And individual sketches can be still very ambiguous to recognize, because sometimes they are very abstract. For example, for this particular example and another example, if you just look them individually, it's difficult to recognize what they are. But when you try to put them into a certain context, then you can easily tell, okay, they are categories. So that motivates us to explore this sketch classification problem by using the context information. So when we was doing this project, at that time, there's no scene level sketch data set. So then we try to extract the scene context from the scene images by assuming the natural scene images, and then sketch the scenes typically have the similar context. So given a set of scene images, we try to extract relation graphs representing the scene context. And then given sketch the scene, for simplicity, we assume the scene has pre-segmented into objects, but we don't know their labels. So individual segmented objects will pass through a CN to predict their individual categories. And afterwards, together with the context, we try to use a compatibility function to improve the classification results. So we try to explore this idea into applications, incremental classification, and the co-classification. So as you can see, this is one typical example of co-classification result. And I think you can see my cursor. So the result here is the final result, and then the result in the parentheses are the original result before the co-classification. So like for this cloud, and they look like very similar, but because it's now the bottom one is somehow is close to the ground, so it's refined as a bush instead of the cloud. And then incremental classification is used more in an interactive scenario, and the user needs to confirm each classification result one by one. But here you can see still when we try to apply the context, we can also improve the classification results. And such context-based approach can be beneficial for like sketch to photo applications. So next, I'm going to talk about our attempts to solve the sketch segmentation and the labeling problem. So this is quite important, particularly because like in the previous context-based sketch classification work, we have already assumed the norm of the segmentation of the input. So here the problem is to given a sketch, we try. Our goal is to segment input a sketch into multiple parts, and in a semantically meaningful way, and at the same time we want to predict the label of individual parts. Our first attempt to this problem was published in SIGGRAPH Asia 2014, and at that time there are quite a few works on 3D shape semantic segmentation, and then there's some existing data set. Basically 3D segmentation data set. So we would like to transfer the segmentation from the 3D models to sketch the objects. And our first approach is purely geometric approach. We try to, given the input sketch and then a set of pre-segmented models, we try to first perform a local interpolation, basically a local matching step. Given a 3D shape part, we try to locally match to the sketch. That will lead to different multiple interpolations. And then in the next step, we perform a global interpolation. We try to resolve the ambiguity in the local interpolation. But this is leads to a combinatorial search problem, and then we use mixed integer programming to solve this problem. And then we get a globally valid structure and corresponding to semantic segmentation results. And then we revisit this problem by applying CAN in 2 years ago, and then our solution was quite simple. I think because like we are not really a machine learning expert, and kind of we are looking for applications of applying decent learning models to our tasks. And so the segmentation network we adopted here is basically very simple UNet structure, and then given a bitmap image, then we apply the UNet and then to predict the segmentation labels. And then in a post-processing, we try to make use of the stroke-based representation. And for refinement, then this is in fact achieved by multi-label graph cut optimization. So visually, we got quite good results. And then so quantitatively, you can see our method beats the MIP auto is our previous solution, and then CRF is another follow-up work, and then DeepLab is a solution for semantic image segmentation. As you can see, generally our solution achieves the better performance than ours non-GC. This is without the post-processing. So that means the structure information in the strokes basically also play an important role. So that motivates us to develop another solution based on a graph convolutional network, and then Qian, and then so the idea is to basically use the structure information in the input sketch, and then so each point basically representing a graph node, and then the edges between points represent edges, then we can form a graph. And besides the static graph built on the input sketch, and so this becomes a local branch in our network structure. And we also consider the structural information between strokes as well. Then the resulting solution achieves quite impressive results, I have to say. And then it's much the accuracy in terms of the pixel-based metric and also the components metric, both are much better than the existing approaches. And this is the result on another data set. This is a Sketchstack 150K data set built on Picture. This data set is, I think the results are quite saturated, and all the methods achieve quite good results, but I think our method achieves the best result. And then next, I'm going to briefly talk about some our work related to 3D interpolation of the sketches. And as you know, the 3D interpolation of sketches, this is L-post problem, because given an input sketch, typically you have an infinite number of interpolations. So, and existing approaches can be roughly classified into two groups of solutions, like reconstruction-based and approximation-based. So the reconstruction-based approaches typically use sketch as hard constraints, and then employ a less constrained shape space. And then on the other hand, approximation-based approach use sketches as a soft constraints and employ a more constrained shape space. For example, this work by Lun et al. Published in 3DV 2017, they given the input sketch. It's typically like a multiple views. They use encoder and a multi-view decoder architecture to predict the depth map and as well as the normal map. And then they diffuse those depths and normal maps into 3D point cloud. This is more reconstruction-based approach. And we have a similar approach. We try to focus on single view normal map prediction. We adopt, I think, quite, network-wise, this is just a conditional GAN, and then, but we also try to incorporate some user interaction into it. I just show you one short video, and so this is a result of our sketch to normal map prediction work. So this is kind of like an automatic way, and then afterwards we also demonstrate user can specify the normals at specific points. Okay, and it's also possible to get 3D models by just simply retrieving the results from an existing data set. So this is a more like approximation-based method, and then you can improve this method by a sampler-based approach. And in this way, like this is our work, the previous CN-based sketch segmentation work. After you get the segmented parts, and then you can try to perform a retrieval, and then for each component, and then you assemble them together, then you get a 3D model. Another work we have done for specifically for animal like head models, and in this case, the shape space is generally limited by the deformation of a template mesh. In this case, is a sphere. So here we assume our output is homomorphic to a sphere, and then we first use a modified version of a pixel to mesh to predict a rough model given one or two sketches, and depicting the object from the front view and also side view. And then we iteratively perform refinement in the view space as well as in the surface domain, respectively done by the VDSNet and then SDRNet. And then finally, we get the refined result. And because of this is kind of like approximation-based approach, so somehow they can tolerate the errors in the input sketch. Another work we had a work, it's called Deep Sketch here. It's a collaborative work with Yuli's group from Zhejiang University. And in this work, given the input sketch, and then we try to predict the 3D hair models. And so we use the 2D and 3D orientation fields as intermediate representations. So it basically contains, for a single view modeling case, it contains two components. First, given the input sketch, we try to predict its 2D orientation fields and also the depth map, 2D orientation field. And then we lift up to 3D by using the O2V net. So this is given the input is of O2V net is 2D orientation field, and then we would like to predict a 3D vector field, basically 3D orientation field. Afterwards, given the 3D orientation field, we can grow hairs from the scalp of the model. And also we try to address the multi-view modeling scenario as well. And we get quite good results if the hair structures are not that complicated. But as you see, when the hair structures are complicated, we typically the results will smooth out the details of the structures in the input. And somehow we are going to address this problem in our recent work for sketch-based hair image generation. So a traditional pipeline for sketch-based hair image synthesis or modeling works like in this way. Just given input sketch, it try to use the orientation map as intermediate representation. And once you predict the orientation map, and then finally you grow the hair from the orientation map. And the problem is orientation maps are not very effective to encode complex hair structures. So these problems can be reflected by a related problem given the input sketch hair image. If we try to get orientation map and then grow the strokes from the orientation map, you can see when the hairstyles are complex, then it's very difficult to get meaningful sketches. So instead of using orientation map, we try to predict the hair images directly from the hair sketch. And so this is our framework. I think network-wise, this is quite simple. And given the input sketch, we first predict the hair mat by using the S2M net. And then given the predicted mat together with the sketch, and we try to predict the hair image directly, and then to get a result nicely blend to the background image. Here we also take the background image and then fuse them at the feature level. To do this, we need a new data set. We propose a data set of this containing 4.5K hair image sketch pairs, and then covering different kinds of hairstyles. And generally our results, I think, are quite good and much better than like the state-of-the-art method, like Michigan listed here. So our result, our method can handle like very complicated, like braided hairstyles, and also wavy. And also compared to Michigan, our method has an advantage of local appearance control as well. And I think this is I think it's the last work I'm going to talk about. That was published in last year. And this is also, our solution was somehow inspired by the previous sketch-based 3D modeling methods, but this time we tried to explore the shape space in 2D And the goal is to generate photorealistic face images from freehand sketches. And to handle rough sketches or incomplete sketches, we basically learn the manifold for face components. So this is achieved by very simple autoencoder structure. And for each face components, we use an autoencoder structure. And then in the latent, once we get the feature space, we can try to perform a manifold projection. This is, we assume, okay, the space is locally linear, then we can perform locally linear embedding to refine an input sketch. Okay, like as illustrated here, given a feature vector corresponding to the input sketch for a specific face component, we basically retrieve the k nearest neighborhood and then perform interpolation. And generally, this works very well. It's very simple, but this works very, very well. Okay, in this, the results here basically show you the advantage of the combination of retrieval and interpolation. So at the top, this is a global retrieval result. And you can see by using global retrieval, you can finally get very good image synthesis result, but it does not really forcefully respect the input sketch. With a component level retrieval, and the generated images they look closer to the input sketch, but you can still see some the difference in terms of details. And finally, this is our component level retrieval and interpolation. To try to balance the faithfulness to the sketch and also the quality of the final result. Because our goal is in this work is to handle rough or input sketches, and this set of results demonstrate, okay, somehow we achieved the original goal. So lastly, I would like to just briefly discuss several challenges and opportunities in this domain. I think one of the important aspect of the current is the sketch data set. Compared to the image data set or video data sets, the sketch data sets are, I think, we need more sketch data sets. We need data sets with larger scales, or multi-view, or different levels of abstraction and deformation. And seeing level like sketch data sets or like sketch data sets targeted for specific applications, for example, sketch-based 3D shape reconstruction, for example. In recent years, we have a few new data sets introduced by in the research community, like sketch scenes and an open sketch, but still, we need more data sets to really advance the field. And in terms of other opportunities, so in this talk, I show you, okay, by employing the structure information of the sketch, we can often improve the performance of the sketch interpolation. So as shown in the sketch segmentation task and also the sketch recognition task. And so given really many very nice methods designed for image understanding problem, how can we basically adapt those methods for sketches is quite interesting problem. How can we make use of the information, the unique features of the sketches? And also personally, I'm very interested in exploring the sketch understanding. Try to do this sketch understanding beyond the 2D sketches. For example, given the time information, of course, you can do a lot of more, like this is related to the animation task in the graphics domain. And also nowadays it's easier to get 3D sketches, and then with the 3D sketches, of course, many tasks we perform for 2D sketch understanding, maybe they are not that relevant, but we are basically we need to handle unique problems with 3D sketches. And this is a list of the publications related to this talk. I would like to thank my collaborators and the students and then the funding agencies. And lastly, I'm happy to take questions from the audience. Thank you for your time.
Okay, thank you, Professor Fu. Let's see if people have questions for your talk. Okay, may I ask one question first?
Sure.
Yeah. So in fact, in my opinion, you have done lots of great works. And my question is, what fundamental questions, in your opinion, haven't resolved in the research field of sketch understanding, like fundamental questions?
Yeah, I think for some, generally maybe for the understanding part, like more towards the analysis part, the solutions are, yeah, generally they achieve very good performance. But for the generation part, I think the current approaches are less mature. I think like particularly for, I think sketch-based 3D modeling, and this is a long-standing topic in the graphics domain. And well, there are many solutions there, but most of the solutions, basically they are quite specific for, they are specially designed for specific models. And they still, we are lacking a more general like a solution for 3D interpretation of the sketches. Just like as I presented, like I talk about like the solution for hair modeling or the solution for animal head-like models, but maybe there are some other solutions by other groups, maybe for parametric models, but still, as you see, the key question is how to balance the generalization or generalization ability and the quality, right? If you target a specific like types of models, and then you generally get better results. But if you want to handle more categories of models, and generally, I think we would like to have a more general approach. But yeah, this is, I think so far, yeah, to me, it's quite important problem.
Thank you. Let's see, lots of people raise hands, right? Professor Song.
Oh, I think maybe Ivan's before me in the chat, but I don't know whether you want to handle me first or the chat first. Anyway, so maybe yes. Sorry, Ivan, if you're before me, but I'll probably just jump in, right? But thank you, Hongbo. I have lots of questions, but I'll choose one, in the interest of time. So I'm quite interested in this sketch, 3D sketch in the AR and VR era. It's not coming yet, but it's definitely coming. So I'm trying to gauge your opinions on, what can Sketch do in AR VR in terms of HCI? Because your group is quite unique in terms of you do graphics vision, but you also do HCI, right? I really want to hear your thoughts on 3D Sketch in AR and VR.
Yeah, I think of course, the most straightforward like thing you can do is the 3D like modeling, and then you can do 3D sketching, right? Just this is for free somehow. Originally, like you needed to do, given the 2D sketch, you need to infer the depth information. Now you have the 3D sketch as input directly. Then it's easier to do 3D sketching and also use a 3D sketch to do 3D modeling. but of course, the works we have published, they are related to mobile AR, and then the input sketch, they are not that accurate. So one of the issues here is how to basically resolve the errors in the input sketch. And there's some other researchers, they are working on also sketch-based shape retrieval in AR or VR. And then, then of course, now the sketches, they are, it's related to a sketch-based shape retrieval, maybe in 2D. But now I think because of the extra dimension, you can basically play with new interaction methods, for example.
Okay, yep. Thank you. Well, maybe we can discuss a bit more some other day. Yeah, thank you.
And some other questions in the chat.
Yeah, there's three questions.
Yeah, how well is from Ivan? How well does these models generalize for unseen sketches? What can we do to improve the generalization? I presented quite a few models, and for example, for the sketch segmentation, I think it's just like many learning-based models, and then it really relies on the richness of the data set itself. And I think the most straightforward way to improve the generalization is to enrich the data set, I would say. So from Yulia, what would be the next most desirable data set? I think this probably will be discussed in the panel, right?
Yes, but since you're not there, maybe we can use a chance to ask you questions, more questions. Just personally for you, just, I don't know, you don't have to even give an honest answer, so.
Yeah, I don't know, it's, to me, I think it's similar to my answer to Qian. I think somehow for analysis part, I think like the quick draw, like Theo Berlin, I think they are pretty nice. But for currently, I think we don't have really larger scale data set for evaluating, for example, sketch-based 3D reconstruction, like task, right? And this kind of also maybe for generation, in general, for generation purpose, tasks currently, we need definitely we need more efforts to generate this kind of data set.
Do you think we need the data sets of paired data, or it would be enough to have, unpaired data sets, or like a large data set of sketches, large data set of 3D geometries, and then maybe we can propose, I don't know, unsupervised methods? I think also Niloy is asking the same question in the chat. Would you need to have a paired data, or would it be enough to have data set of lots of sketches?
That's a good question. Of course, in fact, for the sketch-based, first for the sketch-based 3D reconstruction, generally you can easily generate a paired data by using the line drawing, rendering, and I think later on probably Professor Adrien will be able to talk about some relevant topic, in our current projects, we always use a paired data. I think it's maybe because but unpaired methods that require unpaired data will be also quite interesting. Then that can somehow alleviate the issues with the limited set, the limited data set problem. And yeah, but yeah, I think it's quite interesting direction, but yeah, so far we haven't really explored this direction. Maybe because, yeah, kind of like a supervised like learning is easier for us. I mean, at least for my students, maybe. And yeah, but it will be quite interesting to explore that direction. Yeah, for sure.
Okay, I think our time allows for one more question. So which question do you want to answer? There are the last second. There is an image to sketch dataset which are released in Multimedia 2020. Oh, okay, that's one. And
this is a comment.
Oh yeah, it's a comment. Yeah.
Maybe Kaya has one question. I don't know. Otherwise, you can also have one more question, the last one, if you allow. Yeah, Kaya, please go.
Oh, hi. Thanks, Hongbo. Very interesting talk. So I'll be very quick. So I have one question is on your R2N work. So you've been talking about using the how to combine the two modality, two representational traits of sketches, both in pixels, raster pixels, and both in another in use that is temporal stream, right? So I have one question is then basically what's the best? You know, is there a really balance between the two that will give us a best representation? Because in my perspective, that the temporal streams, is unique in sketches, but such temporal streams are also very noisy, right? Because they basically, is there a pattern there for us to exploit, or what's your thought on this? Because like the temporal stream, I don't think people in my own research, people do this really hard to exploit some very useful patterns solely from the temporal streams, because people do draw sometimes in random orders. So based on something, what's your thoughts on why do we exploit the temporal stream of sketch representation? Or how does it complementary to the normal way of we are just treating sketches as another raster image?
Right. Yeah, I'm not claiming like temporal information itself is that useful. In fact, I think 10 years ago, I had another work about inverse drawing, and that in that work we try to recover the temporal coherence of a given static sketch. And of course, I think we realized, and also I think realized by many other people, and there are many ways to draw the same sketch. But different people will have different drawing orders, or even for the same person. And then if you draw the same sketch at different times, and then probably you also result in different temporal orders of the strokes. And but in the like our GNN-based sketch segmentation work, and also the previous, we try to use a structured information to improve the sketch recognition performance. I think the most important information is still the structure information within the strokes, not across the strokes, I would say. And but still, like in some other works, I think also including yours, right? I think try to use a sequence-based approach and use RNN to do, for example, the sketch segmentation. But if you simply use RNN, then if you encode the positions in a relative way, then somehow you lose the absolute like proximity information. So that's why combining like RN together with CN, the CN can still keep the original spatial relationship between the points, I think, more easily. So finally, somehow to reach a balance and then improve the performance, I would say. But yeah, I think the temporal order of the points within the strokes, I think definitely they are quite stable, because when you draw a stroke, generally it's from one end to the other end, or the reverse order. but generally it's fixed. And then, yeah, the orders cross the strokes. Yeah, they are less reliable.
Thank you, Hongbo. Yeah.
Okay.